Welcome to this section, which is devoted to physical quantities and units in radiation protection. We look at the world around us and we interpret the world around us by using physical quantities. We measure distances, we measure temperatures, we measure time. And of course, also in the field of radiation protection, and more in general of measurements of radiation, there are specific quantities which are used. In this section, we are going to review the quantities and associate the appropriate units to the appropriate quantities. Sometimes, as you will see in your experience, there is a tendency to use older, obsolete units, or maybe using quantities that should not be used anymore because their definitions and their understanding have changed. This is the case also in radiological protection, and you will discover this very soon with the use of much older units than the ones which are used around the world today. At the beginning of this section, we are going to explore the definition and the meaning of quantities which are used also out of radiological protection. For example, activity, for example, fluence, quantities which can be used for radiation measurements in metrology or in other fields. After that, we are going to introduce quantities which are very specific to radiological protection. And they include the absorbed dose, the equivalent dose, the effective dose, and many others which are very important too, like the personal dose equivalent, or the ambient dose equivalent, or the committed dose. All the topics in this section are reported in a very extensive report of the ICRU, the International Commission on Radiation Units and Measurement. It is the report 85, and in that report, I will read specifically, there are chapters on radiometry, interaction coefficients, dosimetry, radioactivity, and quantities and units related to those topics. And you will see these are things we are going to discuss. Alternatively, you can have a look at the very good recommendations of the ICRP number 103. In that document, the Annex B is specifically devoted to quantities used in radiological protection. You can also have a look at the corresponding chapter 4, which discusses the quantities and units. You will find there is a lot of similarity between the content of the ICRP and the content of the ICRU report. And not by chance, these two institutions, they work together in order to establish quantities and units and use of those quantities and units in radiological protection. If you are using the textbook Atoms, Radiation and Radiation Protection by James Turner, you will find that some of the topics we are discussing in this presentation are in Chapter 12 on radiation dosimetry. However, you will not find all the definitions of all the quantities and units as in the report of the ICRP and ICRU. I have to say that even among specialists, there is frequently a confusion in the definition and use of the appropriate quantities. And I hope that during this presentation, you will be able to grasp and remember the difference in the quantities so you can use in your practice of inspectors the correct quantities and the correct unit in a specific given situation. In this section, we are going to introduce and define several quantities and the corresponding units which are useful in radiation protection. Some of you may find this chapter a bit boring because the definition of quantities may sound not interesting. For this reason, I want to start by discussing the reason why we are doing this, and not by defining quantities. Let's think Let's try to think, as a mental experiment, that there is a radiation source and there is a person situated somewhere around that source, and we want to assess and calculate which will be risks coming from radiation emitted by that radiation source to that person. Imagine you don't have all the structure and all the experience that we already have after 120 years of radiological protection. Imagine what we would need to describe this situation. So, in our mental experiment, we see the radiation source as the emitter of radiation. This radiation is altered somehow by the passage through the shielding of the source, but then it comes into the air and it is scattered all around. The interaction between the radiation and the air modifies the direction of radiation, modifies most probably also its energy, and as a series of scatterings take place, radiation reaches where the person is located. The interaction of the person with the field of radiation is likely to change again the characteristic of that field, because the person by itself is also a shielding. So somehow the interaction of radiation with the person is going to create this additional scattering, to create additional modifications to the energy spectrum of the field. At some point, radiation deposits energy inside the cell or even the molecule inside the cell of that person. Let's forget about the specific consequences. We would like to be able to describe what kind of transfer of energy took place, and as a result of that interaction, that deposition of energy, what is the consequence on the cell's functioning, the cell being part of a tissue, the tissue being part of an organ, the organ being part of an organism. So it's quite a complicated problem. If we go back to our presentation, we want to be able to describe how the radiation source is emitting radiation, be able to describe radiation being emitted, exiting from that source and interacting with a medium, which could be the air, could be shielding, could be anything. A field of radiation interacts with a medium and interacts in a way to reach the position where the target is located. It is additionally modified and deposits energy within that target. If we break down the quantities, the language that we will need in order to describe this phenomenon, and if you think about the descriptors, the language we will need to describe the emission of radiation from the source, you know already that what we will need to know is the rate at which radioactive transformations happen in that source, or if it's not a source, if it is a generator, the rate at which radiation is emitted by the generator. It doesn't matter here, it's not very important. But the rate at which radiation is emitted, the type of radiation. Now, we know that the rate at which radiation is emitted is linked in a radioactive source to the number of transformations. So we know also that this is connected to the concept of activity. We know that different particles can be emitted, so we want to know what is the type of decay in order to describe radiation which is emitted during that decay. We want to be able to describe radiation emitted, but also their energy distribution, and also possibly if there is any modification in that energy distribution due to the source, what is called autoabsorption, We also would like to be able to describe the number of emitted particles from the source as a result of this autoabsorption. So these are some of the descriptors that we would like to be able to use in order to describe what's happening within the source when radiation is emerging from the source. Then there is the interaction of radiation with the field. Now the field, we can imagine it is air, or we can imagine it is a shielding, water for example, or a lead blanket, or a container of tungsten or uranium. It doesn't really matter. The field comes with certain characteristics, interacts with the medium, and changes its characteristics as a result of this interaction. Changes direction, changes energy, hence changes its energetic spectrum. It is modified by the interaction with the field. So we would like to be able to describe the kind of interaction, the type, meaning the atomic, physical properties of the medium radiation is interacting with, because we know that different media have different interactions to the radiation. We have seen that photons, for example, and neutrons, they have different mechanisms depending on the medium they are interacting with. So knowledge of the medium is very important. We would like to be able to describe the energy loss, the quality of energy loss, if it is very intense in a very short path, and the quantity of energy loss. How much energy is deposited and by which mechanism? Is it by direct interaction with the atoms, as it happens with charged particles, or is it by creation of secondary particles, electrons, like in the case of uncharged particles, or even by nuclear reactions, as it happens with neutrons? So we want to be able to have the language to describe the distribution of energy after the interactions take place, and the number of particles which are actually passing through an area, a window we want to analyze specifically. We are going to define this because this is an important quantity in radiation protection. It is called fluence of particles. Number of particles which are crossing an area, a window, a location that we consider our observation point. We also would like to be able to know if there is any disuniformity in the distribution of the field. If, for example, particles are oriented in a specific directions, or if they are distributed, let's say, homogeneously all around 4 pi. These are some of the descriptors, the language that we would like to have to be able to use to describe the interactions between the radiation field and the medium. Then we come to the target. We know that at a certain point in space, there is another modification which is happening because the person is located there. So radiation comes in, finds another medium. It is, again, interacting with that medium, changes properties, and at some point within that medium deposits energy. And we would like to be able to describe how this interaction takes place. Namely, we would like to be able to describe how many particles arrive until there. Again, what is the number of particles going into that window, the particle fluence in that specific position? What is their energy distribution? Again, how the field, the beam field, has been changed by the interaction with the target and specifically in the point. How the energy loss takes place. Again, important to know if it is an intensive mechanisms or less intense mechanisms. And therefore to describe how the radiation field is attenuated by going through the target. We need and we want to describe the structure of the medium, the biological medium in this case. Is it soft tissue? Is it hard tissue like bones? What kind of bone? What kind of skin? And basically, as you will see, the most important phenomenon, which is at the beginning of any radiation risk, will be deposition of energy. So we would like to have descriptors related to the target, enabling us to describe how energy is deposited in that specific position within the target. Maybe we also want to have additional descriptors, because we want to describe radiation risk, so we want to know what happens after radiation has been deposited. So in that case, maybe what we will need to know after the deposition of energy, we would like to describe the damage to the cell, or we would like to be able to describe if this damage is a serious one, which was called in the past a deterministic effect, and today is more appropriately called tissue reaction. Or if it's not, if it is a low quantity of radiation deposition, low quantity of energy deposition, low risk reaction, which falls into the category of what we call stochastic effects. We also would like to know if there are other effects in other tissues which have not been irradiated. This is something you may find a bit surprising, but this is the result of the last, I would say, 15, maybe 20 years of research in radiation biology. That is, in our paradigm that we have described until now, radiation goes to a target point and consequences are happening in that target point. It seems that indeed there are some consequences which appear in other areas which have not been irradiated. This is called abscopal effects or non-targeted effects. It's quite surprising and it doesn't fit with our paradigm. We will go back to this point again later when we discuss effects of radiation exposure. But we would like to be able to have descriptors for that. And also, it's coming out since a long time, but it has been recognized formally by the radiation protection community only in the last years, that there are different responses in different people according to individual radiosensitivity. This is unsurprising, I would say, but at the same time, it's a new element. The paradigm of radiation protection until now has not contemplated the individual response of people. Anyway, what I want to express here is it's not only enough to describe the energy deposition in a tissue. We would like to have descriptors enabling us to describe what is the outcome of that energy deposition. There are many other aspects which also have an influence in how not only the tissue and the organ are reacting, but the organism is reacting. Because we are living organisms and we are in our daily lives subject to a series of other risks. So we would like to be able to describe the effect of radiation also based on males and females, based on the age, based on the characteristic, a person which is a bit fatter and the person who is slim, is there any difference in their way of reacting to radiation exposure? A person who is very active has a very strong and very active metabolism opposed to a person who has not. Different ethnical groups, because their physical characteristics are different due to adaptation to different environments, they may react differently to radiation exposure. Lifestyle, of course, has an influence in what we are doing. Stress, exposure to chemicals, as we already mentioned, individual sensitivity. There are so many confounding factors. Now, to be honest, this last slide is just to complete the reasoning. All these components are not present in radiation protection, but this was a mental experiment for us. This is to entice you to understand the importance of these quantities, what we have called until now descriptors, enabling us to describe source characteristics or field characteristics or target, individual target, dosimetry characteristics. These are indeed quantities, physical quantities used in radiological protection. And this is the reason why I started this chapter with these considerations, because we will use quantities related specifically to the characteristics of a radioactive material in order to express source quantities which describe indeed the emitted radiation from a source. We will use other quantities which are called field quantities in order to describe the interaction of the beam of the field of radiation with the medium. And we will use other quantities which are called dosimetric quantities in order to describe and express the result of the interaction of radiation with the target, with the subject, and as a consequence to the tissue and more generally to the organism. This was just an introduction to this chapter, which you may find a little bit heavy on the notation side, on the physics side, but I wanted to, again, as I said, entice you in thinking that all these quantities are very important in order to understand at the very end how we do radiation risks assessment. At present, we are not assessing risks. We are using doses, and we will define doses. There are plenty of these doses. We use the concept of doses in order to express quantities related to risks. As we have said in other occasions, dose is used as a proxy to express radiation risks. So it is of paramount importance that you understand the meaning of doses, and this is the reason why I insist a little bit more on the physical quantities. So that's all, and now we can dive into definitions of physical quantities, very useful in radiological protection. The first question here is, what is the definition of physical quantity? A physical quantity is a property, a physical property of something which can be measured and can be expressed, quantified, as a number and a unit. So, for example, color is a property of a material, but this color, unless it is expressed in mathematical ways, for example, by the wavelength of the color and so on, the color is a property which is not a quantity, but a quality. It cannot be expressed by a number and a combination of a unit. We would say that my t-shirt is blue. So this description is not a physical quantity. A physical quantity would be, for example, the length of a table, because it can be expressed in terms of a unit, meters, and a number, 1.2 meters. Now, importantly, units can be combined together. So in most cases, the physical quantities are expressed as a combination of units. The velocity of a bullet is 100 meters per second. There are many quantities which are used in radiation protection, and more in general, they are used in the metrology of radiation or in radiation transport, in many disciplines which are around radiation protection. Here you see a list. It is not so important to know all of them, but to give you the idea of how complicated this may become. Each quantity must have a unit in order to express it. Now, for historical reasons mainly, some quantities have more than one unit, and in the recent years, in the last 50 years, there has been an effort to harmonize units used around the world. So in many cases there are old units which are obsolete, but still are alive, because in the practice, older practitioners, they keep using the older units, and there are new units which fail to become popular because the new pupils, the new students, they actually continue to use the obsolete terms that their teachers used when they themselves were young. So you as a younger generation, I think you should really make an effort to try and use only the most recent units, and specifically the international system units. We are going to discuss about that later. But here, let's have a glance at the units. These are some of the units used in radiation description of radiation properties. We will go more in detail later. A very important distinction is between vector quantities and scalar quantities, because there are some properties that need to be described in space. So by giving the indication also of a direction and a distribution of directions. This is done by vector quantities, which provide information on distributions in direction, and these are quite complex quantities, as you can imagine. Sometimes they also depend on time, so they have 4 dimensions. Now, they are used in complex radiation transport theory and applied calculations, but for some of you, you may encounter some of them in the practice, for example, in medical physics practice or in radiation metrology practice. These are some examples as defined by the ICRU, the International Commission on Radiation Units and Measurements, which is an international organization trying to systemize all the quantities and units in the appropriate way, and they are issuing reports which are very comprehensive, describing specifically radiation quantities and units and how to measure them, and also other applications which are very important too. But for us, you see so many vector quantities which are complex and used in very, very specialized fields. Scalar quantities, they describe just the intensity of a specific quantity without providing any information on its distribution in space. So there is no indication of the direction, and most probably these are the most used quantities in the practice in dosimetry calculations for us, because what we will use is a quantity describing a property in a specific point under specific assumptions. For example, that the beam is monodirectional, so we don't need to specify the angular distribution. Or that the energy has a specific energy distribution, for example, homogeneous, so we don't need to describe any additional characteristic depending on space, direction, or time. An example of these quantities are the particle fluence and kerma. You will hear more about them because we are going to describe and define them later. And this is a more comprehensive list of some scalar radiometric quantities, starting from the very simple particle number, which is used, of course, in many calculations, going down to more complicated, like energy distribution of energy radiance. Of course, we are not going to use all of them. This is just to give you, let's say, a reminder that quantities exist, and if needed, go and check quantities in publications. Make sure that you know exactly how they are defined, what is their scope, and their field of application. In some cases, there are important limitations in the use of quantities. And associate, as you see here in this table, for each quantity, associate the correct unit corresponding to that quantity today. We have already seen the definition of activity before, activity and lambda, the disintegration constant. And we also have described that the rate at which a transformation occurs, that is the number of transformations divided by the number of atoms present, is a constant for a defined transformation. So this is the way what I just said is expressed in a formula. Number of transformations over the atoms in a sample is a constant minus, because of course the transformation reduces the number of atoms, so is a constant in the unit time. And clearly, if we move dt under dn and we move n on the other side, we have that the number of transformations per unit time is the product of lambda by the number of atoms present in that sample. So the activity definition, the activity of a sample in a particular energy state at a given time is the ratio between the number of transformations and the unit time, where the number of transformation is the mean change in the number of nuclei in that energy state due to spontaneous nuclear transformations in the time interval dt. This is a definition taken from the ICRU, but this is something that you already have clear now. Number of transformations leading to a specific decay, to a specific transformation in the unit time. This is defined as activity. This is the ratio on the right side, and this is another definition, you remember, lambda multiplied the number of atoms. If we integrate that equation, we obtain the equation which describes the transformation of the number of atoms with time. We have seen this before. So the number of atoms in a specific time t is the initial number considered initial just for our purposes, n0, multiplied by the exponential of minus lambda multiplied by t. Now, if we multiply both terms of this equation by lambda, lambda n is the activity, we express activity and the way it changes with time in the same way. Activity is, so the rate of transformations is an original rate that we consider original. Now, this is A0 multiplied by an exponential in which lambda only is appearing with time. So lambda is important. It is the parameter which defines the rate at which activity changes and radionuclides disappear with time. In the international system, the quantity time is expressed in terms of seconds. For this reason, the inverse of a second, which is, for example, called the frequency in electromagnetism, it is given the special name Hertz in the electrical field. For us, the inverse of a second in this field is called Becquerel. Why is it called like that? Because Henri Becquerel is the French scientist who discovered radioactivity. So, as a way of honoring the discoverer of radioactivity, the quantity activity is defined via its unit Becquerel. Now remember, all the units, when they are expressed by writing, they are with small caps. But if you use the symbol, the official symbol has a capital B and a small cap. And this is by agreement. This is like that. You cannot write Becquerel with a capital B. It doesn't make any sense. There is also another unit for activity, which is an older, obsolete unit, which was called Curie. Curie is, of course, a way of honoring Marie Curie, a very famous scientist, a Nobel Prize for chemistry and for physics, who discovered radium, and she was one of the early scientists in studies related to radiation and radioactivity. Now, this unit has been used for a very long time due to historical reasons. 1 Curie was the activity of 1 gram of radium-226. And it was a very big quantity, because if we write it in terms of the international system of unit, 1 Curie is 3.7, 10 to the power of 10 Becquerel. So quite a big number of disintegrations per second. Please note that this unit is not part of the international system of unit. Now, the international system has been adopted by many countries, and in some countries it's a legal obligation to use units which are introduced in the international system. I know, for example, in the country where I come from, it's not possible to write in a legal document or in legislation a quantity which is not present in the international system or expressed in a unit which is not in the international system. This can lead to a fine. Now, what I know is that the UAE, they have adopted the International System of Units already many years ago, in 1961. So we are bound to use, especially in our work as regulator, the International System of Units. So please remember, activity should be expressed in terms of becquerel. A very important consequence, which stems from the equation that we have seen, the evolution of the number of atoms and the evolution of activity, is indeed the definition of half-life. Because in the practice, nobody would express the rate of disintegration by using the disintegration constant. All of us, we are using half-life. So we have seen how half-life is being obtained. It is defined as log 2 divided by lambda. It's called half-life, frequently expressed as T half. It's the mean time taken by a radionuclide in a particular energy state to decrease to half of its original number. We have seen in an exercise how to obtain this expression of half-life. Half-life is a time, so it should be expressed in seconds. In many cases, especially for very big, very long half-lives, it is expressed in hours, days, years, or in many cases even in more than that, million years and so on. Remember, half-life is specific for a specific radionuclide and for a specific mode of decay. So if a radionuclide, say uranium, can decay alpha or beta with two different branching ratio, that means that there will be two different disintegration constants and two different half-lives. You can see that in the table of nuclides. Normally, in the same case, if there is a multiplicity of possible decays, each one has its different half-life or its different disintegration constant. The half-life, as we have seen previously, is a very convenient way to express how quickly a radionuclide disappears, and this is very clearly exemplified in this graph. So you can see the difference between a slow radionuclide, the red one, decaying with time very, very slowly, and this green, very sharp decaying radionuclide here, who has a much faster rate of decay. So half-life is a very convenient way of expressing the rate at which radionuclides disappear with time. And we have to remember that in this equation, lambda is appearing, but we can, by using log 2, we can express this also in terms of the half-life, of the inverse of the half-life. Let's come now to fluence. Fluence is another very important quantity in radiation measurements and in metrology. So what is the idea behind the quantity fluence? Fluence is a descriptor of the number of particles which are crossing a surface divided by the surface itself. Now, you have to imagine that there is a sphere, a small volume, a sphere of volume dV. Consider one area inside that sphere, which will have a small area dA. And now consider all the particles which are crossing perpendicular to that surface. We call the ratio between the number of particles and the area dA the fluence of particles. So this is the mathematical formula. Fluence, which is indicated by the Greek letter phi, is the ratio between dN and dA, where dN is the number of particles which are crossing perpendicular to dA, and dA is the area of that surface. Note that we are not talking about a vector quantity here. We are talking about a scalar quantity. This quantity, as it is defined, it doesn't depend on time and it doesn't depend on the specific direction. So whichever dA we are taking, independently of its orientation, whichever dA we are taking, fluence in that point, in that volume dV, is defined the same way. Each particle can carry energy because it will come with a certain, let's say, kinetic energy, initial kinetic energy. So if we imagine to consider the energy which is carried by each particle in crossing that surface dA, and we call energy fluence the energy incident on that sphere which has a cross-sectional area dA, that will be the definition of energy fluence, and we can express the energy fluence as fluence multiplied by the energy which is carried by each single particle. That's quite simple. If we have fluence of particle which is phi, each particle is bringing an initial kinetic energy of E, the energy fluence will be phi multiplied E. There is another quantity which is very much used in the practice, and that is called fluence rate or flux. Now, we clearly define fluence without any reference to time, but time can be an important element in real situations where the number of particles is changing with time. Therefore, the flux is defined as the ratio of change in fluence with time, and it's indicated by phi dot, and therefore is defined also an energy fluence rate very much in the same way as the ratio between d psi and dt. Why in the practice fluence and flux are important? Because it's very easy to express reaction rates by using fluence and flux. It can be shown when we have a probability of interaction which is indicated by sigma, and the number of nuclei which is indicated by n, the rate at which a specific reaction with probability of interaction sigma happens is expressed by this equation. So the rate at which a reaction indeed occurs is the product by the fluence itself multiplied by the number of atoms and the reaction probability, which is called macroscopic cross-section. So in the practice, you have seen previously cross-sections and macroscopic cross-sections, which are defined and calculated for several reactions and several materials. If we know the fluence of particles and the macroscopic cross-section, we can infer easily the reaction rate. That's the usefulness of fluence and flux. We come now to the definition of kerma. For some of you, kerma may be a new name, a new quantity you've never heard of before. Now, kerma wants to describe what happens when uncharged particles interact with a specific material. Now, you remember that charged particles interact directly with atoms and electrons of a material, and they slow down progressively, continuously, by the result of this interaction. Uncharged particles, which means, just to remind you, indirectly ionizing particles, like photons and neutrons, they lose energy by creating secondary particles and by the slowing down of those secondary particles which deposit energy in the material. So, kerma describes transfer of energy from uncharged particles, photons and neutrons, to the secondary electrons in that specific material. Kerma is defined as the ratio between the sum of the kinetic energies of all charged particles liberated by the interaction of uncharged particles in a mass dm of a specific material. We will go back to this definition again. So kerma is the ratio of the energy transferred by the mass of a material. When we talk about kerma, we need to specify radiation. We need to specify the material. Kerma of photons of a specific energy in water. Kerma of neutrons in air. So let's read once again. Sum of the kinetic energies, so all the initial energies of the secondary particles, which are created by the interaction of uncharged particles in a mass dm of that material, ratio of that energy by the mass of that material. I thought it was useful to show you in a small animation what this means. So let's consider a target here, and we have an uncharged particle coming in, which is the blue line, interacting in this point, creating secondary particles, electrons, which then travel in the material. They are stopped. Now, but for simplicity, they are just shown this way, but you remember that electrons, when they slow down in a material, can have a very complex and tortuous path. Now, let's consider of these secondary particles, their original energies, original kinetic energies when they are created, and I indicated that with these red spheres here, red circles. We will need to divide the sum of all those initial kinetic energies by the mass, dm, mass of the material, where all these particles are being liberated and slowed down. Actually, the acronym kerma helps you to remember and understand the definition of this quantity, because kerma stands for kinetic energy released in matter. What is the unit? Okay, units are the ratio between an energy, which is expressed in joule, and the mass, which is expressed in kilograms. Remember, in the international system, mass is expressed not in grams, but in kilograms. It's the only unit which is expressed in kilo something. So if we write this down, the international unit of kerma is joule over kilogram, which has a special name in our field, and this is called Gray. Harold Gray, he was a scientist, a British scientist, who was at the very beginning of the 20th century, in the first half of the 20th century, one of the prominent scientists in studying interaction of radiation with biological matter. So Gray is written again like this, and its symbol is capital G, Y. Now the confusing thing, as you will see, is that Gray, the unit Gray, is used for several quantities. So we will need, every time we discuss about a quantity and a unit, to express clearly the name of the quantity and its unit. Just saying Gray, it doesn't automatically explain what is the quantity we are discussing, because several quantities use Gray as a unit. Why such a complex definition for a quantity? What is the advantage of using that definition, which seems to be so difficult already to understand? Well, the reason is that there is a fundamental quantity in radiological protection, which is the absorbed dose that we are going to see later on. But absorbed dose is very difficult to measure. So in the practice, even in a laboratory, you need to have specialized detectors to measure directly absorbed dose. And in a specific set of conditions, kerma can be used as an approximation to absorb dose. And kerma can easily be calculated and measured. So kerma has many advantages. Remember, it is defined only for uncharged particles, so for photons and neutrons, and for a specific material. So we will need to define kerma of photons in air or in water or in whatever material we are considering. Now, there are a series of conditions when this actually happens. This is quite an advanced part for this chapter. I'm putting it here for the benefit of the Radiation Safety Department. Remember, the kerma absorbed dose approximation is not always valid. It is valid in a series of conditions: when charged particle equilibrium exists, when losses by radiative means are negligible, and when the kinetic energy of uncharged particles, so incoming uncharged particles, is large compared to the binding energy of the secondary particles. Now, these three conditions normally are respected, but not always. So there are some conditions in which there is no equivalence between kerma and the absorbed dose. So that approximation is not valid anymore. And this is, for example, the case when there is a strongly and quickly varying field, or at the border between one medium and another medium. This topic specifically is very specialized for the Radiation Safety Department. I'm putting it here just as a reminder to the inspector of the Radiation Safety Department. Kerma is normally a good approximation to absorb dose. Using kerma, as we will see later, allows operational radiation protection to exist, meaning some of the quantities we are going to define are not measurable. You cannot measure them in the practice. So kerma represents a bridge between the world of those quantities that we cannot measure and the other quantities, which are operational radiation protection quantities, which can be measured and can be used in the practice. That's why kerma is so important in our practice, because it is a link between two different worlds which otherwise would not be able to communicate with each other. Very important to remember, what we have defined is only for uncharged particles. For charged particles, there is an equivalent to kerma which is called cema. Now, again, this is a very specialized part. Not all inspectors need to know the definition of cema, but maybe the question comes, what do we do for alpha particles or for beta radiation? Well, there is another quantity which is defined similarly to kerma, which applies to charged particles. Something else I also want to mention is the definition of exposure. This is a quantity which is definitely obsolete today. But in many cases, we still see instruments which are calibrated in exposure or readings which are expressed in units of exposure. And every time I see that, I feel a bit embarrassed. Exposure is an old quantity which had its meaning at the beginning of the 20th century. It has been used for a very long time, but now is useful only in very, very specific situations. So I will not go into the details of the definition, which is a bit complicated. It's related to the charged of one single kind, which are created by photons interacting with a specific mass of air in standard conditions of temperature and pressure. But what I want to stress here is exposure is defined as a ratio between charges, so Coulomb in the International Systems of Unit, and a mass. By the way, it's defined only for photons, not for neutrons, and only in air. So it has a very narrow field of application, and it's not so elastic, and it has not the same meaning as kerma. However, this quantity still lingers on. Please remember that values expressed in exposure, in units corresponding to exposure, are not the same as those expressed in kerma or in absorbed dose. There can be a significant numerical difference, and this unit is today no more in use. It was called Röntgen, and it was the special name of the unit Coulomb over kilogram. So exposure is a different quantity, is defined in a different way. It's defined for a narrow field of particles and interacting medium. It's a quantity which is related to the past. Today has no meaning. Today we have kerma or absorbed dose, which are really much more flexible as quantities. Another quantity This very important in the interaction field. We have already introduced that before. Now let's define it, is the cross-section. The cross-section is a measure of the probability of an interaction, and it is expressed in terms of an area. The cross-section sigma for a specific nuclear reaction is the ratio between n and phi, where n is the mean number of such interactions per target entity subjected to the particle fluence phi. Now, remember, the product of phi by sigma is the mean number of interactions, so we can define sigma as the ratio between the number of interactions and the incoming particle's fluence. Units of cross-section. Cross-section is an area, because it is the ratio, let's go back, it is the ratio of a number of particles divided by a number of particles, which is divided by an area, so it's an area. And indeed, it is expressed most frequently by a special unit, which is called barn. The barn is equal to 10 to the minus 28 square meters. So, of course, it's a very small quantity because interaction rates, interactions probabilities are very small in the nuclear physics area. Now, if you remember at the very beginning when we discussed the size of an atom, we said that the nucleus has the size of 10 to the minus 15 meters, which has a special name. It's called Fermi, as a honor to the Italian physicist Enrico Fermi, who for the first time conceived and operated a nuclear reactor, and before that made a lot of studies in the nuclear fission area. So 1 Fermi is 10 to the minus 15 meters. 1 barn is 100 Fermi square. So 10 to the minus 28 meters square. You know why barn is called like that? There is a story. They say that in the beginning of nuclear physics, in the early years, scientists were studying, as they are doing also today, and measuring cross-sections of different reactions. And one day they came to the fission reaction with thermal neutrons. And they were used to have very small numbers, but in that case, they noticed that the frequency, the probability of interaction was huge, so huge that somebody must have commented, it's as big as a barn. So they say, maybe this is a legend, I don't know, but it's a way to remember the unit of cross-section, which somehow expresses a small quantity in a very, very small world. Some examples we have seen previously. These examples, these are cross-sections related to nuclear reactions. This is the N-gamma reaction on plutonium-239, and you can see that it has on a log scale, on a log-log scale, a typical linear behavior, with the exception of specific areas. It doesn't really matter here, the explanation. What it's important is to have a look at these probability of interactions plots. This is another reaction. It's photoneutron reaction, gamma N over iron. This is clearly a reaction which has a threshold happening with a maximum value around 15 megaelectron volt and then decreasing, probability decreasing again. And this is another example of cross-section. This time it's the interaction of a gamma beam over carbon, where we can see that the behavior is dominated by the photoelectric effect in the lower energies, then by the Compton effect in intermediate energies, and by pair creation in the higher energy range. We come now to a very important part of this quantities and units section, which is a discussion over doses. And as you will see, dose is a concept which is declined in a number of different doses. Unfortunately, some of them, they have very similar names, so we need to remember and understand their definitions. And as I mentioned before, unfortunately, sometimes the same unit is repeated over different quantities. So this can be confusing, and this is the reason why I think it's important for all inspectors to have clear ideas on the definition of dose quantities. There are several doses. Absorbed dose, which is traditionally indicated with letter D, equivalent dose, H, effective dose, E. Be careful, in the past, a dose equivalent had also been defined, and also a dose effective had been defined. Personal dose equivalent, HP, is also an important dose, and so is ambient dose equivalent, H star. These two quantities, equivalent dose and effective dose, are most important for us at FANR as regulators. They are called protection quantities, and they are used while defining those limits or those constraints. They are a way to ensure protection to humans. So those limits, as you will notice in the regulations, are expressed in terms of effective dose over a year, or equivalent dose to specific organs over a year or multiple years. There is only one caveat here. Those two quantities, as we will see by their definitions, cannot be measured in the practice. That's why other quantities, including HP, the personal dose equivalent, and H star, the ambient dose equivalent, have been defined, and they are called operational quantities. Those operational quantities, they allow to do radiation protection in the practice, allow to measure fields, allow to evaluate risks, but they are connected to protection quantities, so they are very important in the practice. And why am I mentioning this for you as inspectors? Because in the practice, the calibration of instruments is done in operational quantities. Of dosimeters, it's done in operational quantities. It is not done in protection quantities. Let's see now the definition of absorbed dose. I have repeated, I think already many times, how important it is to describe the deposition of energy, because that's the fundamental moment in the beginning of what will create radiation damage and harm to an organism. So absorbed dose is exactly answering to that quest. So it's a way of describing how much energy is deposited in a material. The formal definition is this one. Absorbed dose D is the ratio between the mean energy imparted by ionizing radiation to a mass dm of a matter of material. The definition is written this way, with this formula, by the International Commission of Radiation Units and Measurements. So you can appreciate that this is an expectation value of an energy over a mass. So the units of absorbed dose are, again, joule over kilogram, and we know that this is a special name, has a special name in radiation protection, and it's called Gray. In the past, a different unit was used, which was called rad. The definition of that unit was different, and it was connected to a different way of assessing absorbed dose. So it is not today encouraged, actually it is deprecated. It should not be used anymore. There is a relationship, an exact relationship between rad and Gray. 1 Gray, which is bigger, is 100 rad. A few considerations on absorbed dose, a few important observations. The first one, absorbed dose is a fundamental physical quantity for radiation protection and for many other disciplines as well, which are around radiation protection. So for radiation biology, for radiology, in some cases, for example, in the practice of radiotherapy or when assessing the effects of incidents and accidents, that is the quantity which is used. When we are discussing high doses related to tissue reactions, it's absorbed dose which is used. It's not equivalent dose or effective dose. So it has a very important application in the practice, specifically in the medical field and in fields related to incidents and accidents. This quantity is defined for all kinds of radiation in any irradiation geometry. And for this reason, as we will see, this is a physical quantity. It has all the requirements to be considered a basic physical quantity, and indeed, this quantity can be measured. There are instruments, there is a specific laboratory setup with very advanced instrumentation, which allow scientists to measure the deposition of energy by way, for example, of some chemical phenomena or maybe some increase in the temperature of volume of water. Calorimeters are used to assess the deposition of energy. But these are very, very specialized instruments. Normally, that quantity can be related to physical quantities, so can be also measured and assessed in a laboratory. As I say here, it should not be used at the microscopic level, at the level of an atom. It should be used on a, let's say, a larger volume than a single atom, because it's an expectation value. It's a quantity which is defined over a large volume. It is a measurable quantity, and there are standards which allow their determination, as we have said. But we also discussed in the previous part that there are mechanisms which underpin the interaction between radiation and matter. We have seen that radiation can interact by exciting atoms and nuclei, by ionizing atoms and nuclei, by damaging the structure of a lattice or damaging the structure of a molecule. So the deposition of energy is not a quantity which is sufficient to describe what is the result of that interaction. Moreover, there are very significant differences between the interaction of charged particles, which, as we have seen, interact directly, continuously with a material, and in the case of alpha and proton, it's very intense as interaction. It's a very intense ionization by a unit path, and uncharged particles, photons and neutrons, which create different kind of reactions and create particles, secondary particles, which then slow down as betas. So it's not only a question about describing how much energy is deposited. It's also a question to describe how this deposition is actually happening during an interaction. So from absorbed dose, we move now towards another quantity which is called equivalent dose, and which describes the way the interaction takes place in the material. So the radiation and its way of interaction with the material. Now, how can you describe this quality of the radiation interaction to a material? Well, in the past, indeed, the quality of that interaction was expressed in terms of the so-called linear energy transfer. If you consider the path of, say, a beta particle, how much energy is deposited along that path, the linear energy transfer is a ratio between the energy deposited and the length of that path. There is a quantity which is used in micro dosimetry. I introduce it here just for clarity because you will see a couple of tables later. So this linear energy transfer is the ratio between the energy deposited and the linear path, where delta has a very specific meaning that we don't need to go through in this presentation. We also have noticed and repeated here that radiation interactions can be expressed in terms of charged particles and uncharged particles, and therefore can be described in terms of low linear energy transfer, low LET, or high LET interaction. As a result, in the past, there was a factor which was called quality factor, which was indicated by the letter Q, and was indeed varying. It was a function of the linear energy transfer. And that quality factor in the past was used in the definition of dose equivalent, be careful, not of equivalent dose. Previously, and that is the reason why I'm telling you this now, the previous quantity, dose equivalent, in the past was defined by using the quality factor, which was based on the linear energy transfer. So that was an approach. That quantity was defined, dose equivalent, and it had its specific unit. Today, as you will see, equivalent dose is defined differently. It's not defined on the simple deposition of energy, the linear energy transfer. There is an additional component that we are going to see. But now, let me show you those tables I mentioned before. So this is the linear energy transfer. We call it here in a more complicated way, but let's just consider the last column. This is a beam of protons interacting in water, and this is the linear energy transfer for protons of different energies. The unit here is megaelectron volt, not over a length, but megaelectron volt square centimeters per gram. Why that? Because also the density of the material is introduced in this definition in order to uncouple the final numbers from the density of the material considered in the table. So if we have a look at the numbers here, what we notice first of all is that these numbers decrease with energy, which means that protons of higher energy per unit path, they deposit less energy than protons of lower energy. And we know this. We know that charged particles, you remember that graph showing the Bragg's peak? In the beginning, when they enter a material, they have higher kinetic energy, and they create less ionization, which deposit less energy, it means. And then the number of pairs goes up onto a peak, and then they drop to zero. Now, the peak happens right before dropping to zero, so stopping the particle, which means that the deposition of energy of particles which are slowing down is much more effective. And this is indeed reflected in this table. A similar table here, we have electrons, not protons, again in water. And you see, again, we look at the last column, we see the same trend. That is, for higher energies, the deposition is less, and then it increases by reducing energy of the electron. Okay, this is counterintuitive. We would think that the deposition of energy will be higher for higher electrons, higher energy electrons, and indeed it's the opposite. Less deposition per unit path for higher energy electrons, higher deposition of energy per unit path for lower energy electrons. Now, in these tables, I will show you in these two following tables the relationship between the quality factor and LET. That's just to give you an idea of how that quantity was defined. The quality factor was used in order to express that quantity, and that quantity depended, as you can see, directly from the LET, so from the deposition of energy. This was the setup as suggested before 1990, and this was the dependence after 1990. This is not so important for inspectors. The point I want to stress here, there was a direct relationship, as you can see, for example, in this graph, where the two approaches are compared. There was a direct relationship between the linear energy transfer of a particle interacting with a material and its quality factor, hence its dose equivalent. This approach was changed into the quantity we are using now, which is equivalent dose. Again, I want to stress all these technical aspects are relevant maybe more for RSD inspectors than the others. Just take these as part of your radiation protection culture. You don't need to remember all the details. Just remember the approach. previously, dose equivalent was defined in terms of the linear energy transfer. Today, equivalent dose, as it was defined in the recommendation 60 of the ICRP, International Commission of Radiological Protection, it is defined in terms of weighting factors, and these weighting factors are a function of the relative biological effectiveness and no more of the linear energy transfer. So this is the reason why I insist quantities should be used with their definitions and their units, because the underlying assumptions and the way they are defined can change dramatically. It seems just swapping the words doesn't change nothing from equivalent dose to dose equivalent, but indeed there is a very, very different approach. Let me quickly show you what is the approach of the relative biological effectiveness, and we will see the weighting factors as well. Relative biological effectiveness is a way of judging what is the amount of radiation generating the same effect in a population of cells than a given amount of reference radiation. So, for example, consider photons of a certain energy impacting over Petri dishes over a population of cells with a defined absorbed dose giving a certain consequence, like a death ratio of 60% of the cells. Now we take another radiation and we want to assess what is the amount of that radiation creating the same effect, the same 60% death ratio in the Petri dishes as the reference radiation. The relative biological effectiveness values are given as the ratio of absorbed dose of two types of radiation producing the same biological effect in identical irradiation conditions. So, dose value of a reference radiation, our original gamma radiation of a certain energy, divided by the corresponding dose value of the considered radiation that we want to assess. So, you see, the approach is very different. We don't consider simply the deposition of energy, the linear energy transfer. We are considering a different endpoint, the same biological consequences in the Petri dishes. You remember before we discussed about protection quantities and operational quantities. And we also have said that protection quantities are used in regulations to fix exposure limits for population and for workers. Now, specifically, we will go into this discussion a bit later, but here I just want to remind you the two concepts behind protection quantities. Limits are specified in order to avoid tissue reactions, which are highly dangerous and very severe effects on tissues and organs, and in order to keep stochastic risks to a lower level, the most reasonable level achievable. These two concepts are expressed on one side with the equivalent dose and on the other side with the effective dose. So equivalent doses, which, as I mentioned, are used in incident management or in medicine, are used to express dose limits to tissues and organs. And in the regulation, you will find equivalent dose annual limits for the lens of the eye, for the hands, for the wrist and forearm, for the feet, for extremities in general, and for the skin. So these are the organs for which equivalent doses are defined. The definition of the protection quantity, equivalent dose, is based on the average absorbed dose D in a tissue T, or an organ, due to the radiation R. So we imagine that into a tissue named T, different radiation are depositing energies, so we need to consider all the radiations depositing energy in that tissue, and that will lead us to the definition of the protection quantity equivalent dose. The protection quantity equivalent dose in an organ or tissue is defined as the sum over that tissue of all the radiation depositing a certain absorbed dose multiplied by the corresponding weighting factors. Okay, don't be intimidated by this summation. This means, let's suppose that there is only one radiation, only photons. And the photons deliver to the organ, only to one organ. Let's imagine the hands. A person is exposing her hands in a beam. They deposit a certain absorbed dose. What we will need to do in order to calculate the equivalent dose is to multiply the weighting factor for photons by the absorbed dose due to photons on the hands. So it's just one term. But if you have multiple radiation, then we will need to consider each single radiation with the absorbed dose that that single radiation deposits in that tissue. WR are called radiation weighting factors for the specific radiation R, and the summation is performed over all types of radiation which are involved in this deposition of energy. These are the recommended radiation weighting factors by the ICRP, as mentioned before, the International Commission on Radiological Protection, which have also been introduced into the UAE legislation. Let's have a look at them. It's important to understand. The numerical values are very simple. They are rounded up. So for photons, irrespective of the energy, the weighting factor is 1. For electrons and other particles, it is 1 as well. But for protons and also other particles, it is 2. For alpha particles, fission fragments, heavy ions, so those particles who create a lot of damage in their interaction, it is 20, which means much higher than the photons 1 or the electrons 1. Neutrons, well, neutrons, as usual, are a bit more complicated, so they have a curve which depends on the energy. Now, come back to the previous slide. No energy dependence for every particle, with the exception of neutrons. For neutrons, weighting factors goes to this value, which is around 2.5, goes up to 20, actually more than 20, and then it drops down again for higher neutron energies to some units. There is also a mathematical expression for this curve, and this is the mathematical expression. It's not so important here for us, just to let you know that this exists and it is available if needed. The units. We have said that units here are energy over a mass. So the International System unit for equivalent dose is joule over kilogram, but it has a special name, which is sievert. And again, this is a respectful homage to Rolf Sievert, who was one of the first scientists to study deeply the effects of radiation on biological matter. Sievert is written like this, like the name of Rolf Sievert, and it is in the acronym capital S and V. As you may imagine, there is also an older unit which is deprecated, and we encourage not to use it. That was the REM. The acronym for REM was Röntgen Equivalent Man, so you can already appreciate it was defined as a reference to the Röntgen, which is the unit of exposure. So it's a very, very old unit that should not be used today anymore. Again, there is an exact relationship between 1 sievert and REM, it's 100. So the sievert, as the gray, is bigger than the REM, as the rad, and the conversion factor is 100. Let's have a few observations on the equivalent dose. So we have said that absorbed dose is a description of the deposition of energy. equivalent dose adds to that description a weighting factor which describes what is the particle depositing energy, so what is the additional value of the mechanism of energy deposition. 1 gray of absorbed dose by electrons and photons is, remember the table, 1 sievert of equivalent dose for electrons and photons. But the same 1 gray of deposition of energy by alpha particles is indeed 20 sievert in terms of equivalent dose. So this quantity expresses not only the deposition of energy, but also the relative effect that the mechanism of interaction has in generating harm, in generating a biological endpoint. The equivalent dose is not a basic physical quantities, because it is the result, remember the definition, of a summation of a product between a physical quantity and a dimensional factor. As a result, equivalent dose cannot be measured, and that's the main difference with respect to absorbed dose. Let's also notice that the WR, the values of WR, those numbers which are rounded 1, 2, 10, 20, those are selected by judgment, by experts around the world. It's the result of consensus, of expert consensus. And they are based on a series of very complex and very diverse experimental relative biological effectiveness data. And therefore, they are not obtained by statistical methodology only. They are a result of a judgment, an expert judgment, a digestion of those data by experts. I want to stress, you have already heard this before. Previously, protection quantities were defined in terms of the linear energy transfer and the quality factors, and that gave the dose equivalent. Today, the equivalent dose is defined in terms of weighting factors. In these tables, you will see a comparison between the weighting factors of the newest recommendation in 2007 and the recommendation in 1990. So how they have evolved over time. This is more specialized observation for RSD inspectors. So previously, in 1977, dose equivalent was defined in terms of a quality factor which was based on the LET. Then, in 1990, equivalent dose was introduced, and it was defined by weighting factors based on the RBE. In 2007, the same concept was maintained, but the weighting factors were revised. In the regulation, today, in the FANR regulation, equivalent dose is defined by using the weighting factors of the latest recommendation, 2007. The path that we have seen, that we have gone through until now, describes deposition of energy, different weighting of the energy deposited depending on the mechanism, but where do we account for the biological effect? This is the third most important quantity we are going to define now, and it's again a protection quantity, and that will be effective dose. How do we express the outcome, the end point of the energy deposition in an interaction with a specific tissue? We will use, starting by the equivalent dose, we will use other factors to define the so-called effective dose. Let's see the definition of effective dose. The protection quantity effective dose is defined as a weighted sum of tissue equivalent doses. This way, again, don't be discouraged by the summation. This can be very easy if we read it together. So first of all, let's have a look at the first summation here. It says that the effective dose is the summation over all the organs. So let's consider only one organ to start with. We need to multiply that organ weighting factor by the equivalent dose in that organ. So if we have, let's say, only one organ, let's give the example of before, the hands of an operator which has exposed his hands in a beam. We will use the weighting factor for the hands, if it exists. We multiply it by the equivalent dose in that organ, in the hands, and we will obtain an effective dose. Now, this equivalent dose to the tissue or organ T is indeed defined as it is in the second summation here. It's as we know, the summation of all the weighting factors for radiation of the absorbed dose in that tissue or organ due to that radiation. Now, this is just a more complicated way of expressing it. If we have multiple radiation and if we have multiple tissues, then the summation is extended to all the radiation and to all the tissues. Interesting thing, but not surprising, the tissue weighting factors, they sum up to 1. Because each of them, they represent the contribution or the component due to a specific organ. So you can imagine the hands, the skull, parts of the body, which are not necessarily geometric, as simple as what I said, but they sum up to a unit. The unity is the body, the human body. And here we just repeat what we said before, so we need to perform the summation of the equivalent doses in tissues over all organs and tissues sensitive to the induction of stochastic effects. This is something we are going to discuss a bit longer later. That is, effective dose is defined only in the realm of low doses. And it is defined in order to measure risks related to little exposure to radiation, not to high doses. Therefore, it refers mainly to the induction of stochastic effects, while for the induction of higher effects like tissue reactions, it is recommended to use absorbed dose, as I mentioned before. Let's have a look at these weighting factors. These are the weighting factors that were introduced in the recommendation of the ICRP in 2007. And as you can see, several tissues, lung, stomach, colon, bone marrow, breast, are put together, 6 of them, each one having a weighting factor of 0.12, of 12%. This means they contribute, each one of them, to 12% of the effective dose. But the 6 of them taken all together, 6 multiplied 0.12, is 72% of the contribution comes from the irradiation of these organs in the body. Now there is a definition for remainder, which I didn't put because it contains a number of smaller organs, so I didn't want to complicate too much. Gonads, reproductive system, is one single organ, and it has a weighting factor of 0.08, 8%. Those other 4 organs, they contribute 4% each, 16% in total. And the remaining glands and bone surface, skin, they also contribute, but very little, 1% each, so 4% in total. This is the contribution that should be considered, the weighting factors for tissues that should be used whenever one wants to calculate the effective dose due to a specific irradiation. Just for your knowledge, this is another table which puts into comparison the evolution of these values from 1977 to 1990-91. So we can see an historical trend. This is more important for radiation safety inspectors. Effective dose units. Again, the unit is a joule over kilogram. And unfortunately, the special name is again sievert. This can be a little bit confusing. In this case too, rem was used in the past. Its use, as I mentioned, is deprecated today. We will discuss more in detail in the paradigm of radiation protection what is the extent and the importance of effective dose. However, I want to stress here the importance of this quantity, which is again not a physical quantity. It is a quantity created by assembling equivalent doses and weighting each one of them by the relative importance of tissues and organs in the human body. This quantity has been developed, as we write here, to express in a quantitative way the probability of stochastic effects on the human body. And it should be used both for external exposure and for internal exposure. It is a broad quantity. It is a practical radiation protection quantity, which is, first of all, a pragmatic radiation protection quantity, and involves judgments in the definition of the weighting factors, so the values that should be used for the calculation. First of all, similarly to equivalent dose, it is not a physical quantity. It cannot be measured. Second, it is a quantity of paramount importance because it allows to establish, as I mentioned before, judgments on the risks due to irradiation, both from internal and external radiation fields. Therefore, it is an important quantity which is normally indicated as a contractual quantity in fixing risk management for exposed workers which are exposed to the risk of radiation. Due to the fact that there is a dimensional factor, as said, this is not a physical quantities. The single values of the weighting factors or on tissues are selected by expert judgment. A few other considerations which will help you to understand the extent of the use of effective dose. The values were chosen as a result of analysis of population and epidemiological studies on the induction of cancer into huge populations, and also research made on organisms. The values, they are, of course, the result of averages. These are average values which are averaged over both sexes and all ages, and therefore they don't relate to the characteristic of a specific individual. The kind of information that we receive from the use of effective dose is not individual related. Effective dose should be used in prospective assessments, that is, in analyses which are done before the actual exposure takes place, and they should be used as a way of, as we say, optimizing the radiation protection of a specific activity. It would be very wrong to use effective dose as an individual assessment of risk, and this is a use of effective dose which is discouraged and should not be done in the practice. Now the question is, what is the result of exposure to radiation? This will be the content of the next chapter, the next section, which is devoted to describing the effects of exposure to radiation in biological systems. And we will see better what is the link there between exposure to radiation, equivalent dose, and effective dose. So take-home messages from this section is there are several quantities which are used in radiological protection. Some of them describe the emission of radiation from a source, and they are called source quantities. Others, they describe how radiation interacts with a field. They are called field quantities. And other quantities define the deposition of energy and help in defining dosimetry. So they are related to the concept of dose. We have seen by now at least 3 doses: absorbed dose, which describes deposition of energy; equivalent dose, which introduces the mechanism by which deposition of energy happens; and the third one, effective dose, which takes into account the outcome, the endpoint of irradiation. And these two, equivalent dose and effective dose, are called protection quantities, and are used in the regulation as a way of establishing limits and constraints on the exposure of workers and members of the public. There are units which go along with each of the quantity, and I have explained how important it is to specify the unit and to have a clear idea of the definition of the physical quantities used in radiological protection. In the next section, when we are discussing the effects of radiation exposure, we will put together all these concepts and all these quantities that we have defined, and we will see the usefulness of having specific quantities related to the deposition of energy, another quantity describing the mechanism of deposition, the mechanism of interaction, and the third quantity, which is a more, let's say, broad quantity describing the effects on the organism. This is the end of the section, which was devoted to physical quantities and units. In this section, we have seen quantities and units used in radiological protection and in other fields, important ones like half-life, like activity, and more specialized quantities like kerma, for example, and others that are used much rarely like cema. But most importantly, in this section, we have defined and explored the various meanings of dose. Dose, as you have seen, is not a single concept, a single quantity. There are numerous definitions of different doses, and some of them are very important for the practice of radiological protection because they are used in the daily activities. We express those measurements by using millisievert or millisievert per hour. But what is the quantity that we are actually referring to? I hope you have clearer ideas now. The next step in our program, in the next section, is to explore the current organization of the radiation protection system, what I call the paradigm of radiation protection today.